So in this chapter and in the next few chapters, we will discuss a very, very important machine learning modeling framework called neural networks. And these are so important today, especially since 2012, that there is a whole area called deep learning. There is a whole area called deep learning, which has become extremely popular part of machine learning today. It has created such huge impact on society and businesses that will come to deep learning in a little while. But before we understand this whole area of neural networks over the next few chapters, let's get a little perspective on the history. Understanding the history will give us a much more better appreciation and understanding of neural networks themselves. So the very first simplest model, which we can call as a neural network based model, is called perceptron. That was designed in 1957 by a mathematician called Rosenblatt. Very, very interesting model. And we'll see in the next few videos in this chapter itself, we'll see what a perceptron is and how a perceptron is very similar to a logistic regression with the small changes, right? So a perceptron can be imagined like a logistic regression with a slightly different loss function, with a slightly different, little bit of difference between perceptron and logistic regression, but intuitively they're very related. Okay, we'll get to the exact differences and relationships between perceptron and logistic regression. And this was in 1957. Remember, in 1957, just after Second World War, when a lot of research was being done on translating from, especially in the US, because of the Cold War, people were trying to translate from Russian to English. So there is a lot of research on what intelligence is and how to build intelligent systems. Some of the greatest minds of their generation, like Alan Turing, the father of modern computing, right? All these people were asking these very, very interesting questions on what is intelligence and how do we create it artificially in this new machine called a modern computer that was being built around Second World War, at the end of 1945 and around in the 1940s and 50s, right? They said, how can we create intelligence in a computer? So what they've done is they said, we have some understanding of what a neuron is. And remember, for all of these people, there is a biological inspiration. There is a biological inspiration, right? Because we know that humans and many animals, right? Humans, monkeys, right? Even ants, right? Lots of these animals and creatures have some form of intelligence. Of course, humans, to the best of our knowledge, are the most intelligent creatures on earth today. But there is a lot of inspiration because we all know that thought happens in our brains, right? And there is some, because of a lot of research in neuroscience, there is some vague understanding of how the brain works. A very, very vague understanding. Very, very vague understanding. It's not clear. But they know that there is something called a neuron. There is something called a neuron, which is the basic building block, And let's see how a neuron operates, right? So this is a very nice example of what a neuron is. Okay, a neuron has something called a nucleus. Okay, this is a biological neuron. Okay, a neuron has something called as a biological nucleus, and they have something called as dendrites. This is also the cell body, right? Now, it also has these things called dendrites. So what happens is, when a neuron gets electrical signal inputs from these dendrites, it does some computation inside, okay, and it sends these electrical impulses outside towards other neurons. So you have these neurons like this, which get a lot of inputs from through dendrites. Neuron does something internally, right, within its cell body, and it sends out pulses to other neurons. This is the most simple way to understand a biological neuron. A biological neuron actually is a very, very complex machine. It's a brilliant machine. When I studied about biological neurons when I was learning from books and also while taking some courses at graduate level, I understood that it's a massively complex structure internally. But if you want to simplify it, the simplest way to understand it is there are some electrical pulses coming inside, some signals coming inside, some electrical pulses. It does some computation inside and it sends out signals to other neurons. And some of these are connected to other neurons, right? This is another neuron. So this output becomes an input to other neuron, right? So this is the basic structure of what a neuron looks like, right? Very, very simple structure. And if you want to represent it mathematically, you can say, imagine if I have inputs x1, x2, x3, x4, right? People said, can I somehow represent this whole idea of a biological neuron into a mathematical form? Remember, Rosenblatt and others were actually mathematicians, were actually hardcore math people, right? Who were trying to say, can I somehow get a very, very simple model of a neuron and put it into a mathematical structure? So they said, imagine if I have some inputs. This is my cell body, right? My cell body takes all these inputs. Of course, some inputs are more important than other inputs. So let's put weights on these inputs, right? Some inputs will be more important than other inputs, right? And this is also understood in the biological neuron structure. Some of these impulses, some of these inputs tend to have more importance than others. And these are observations from biological neurons. So they said, let's build a very, very simple model of it. So the biological neuron looks like this, the artificial neuron, or the computational neuron, or the mathematical neuron looks like this. You get a bunch of inputs and you decide which one to give more importance by using these weights, right? All these are inputs. Now, when I get all these inputs, I'll summate all these inputs, right? So I'll do W1 multiplied by X1, because W1 is the weight I'm giving to this input, right? W2 is the weight I'm giving to this input, right? So what I'll do first is I will summate all these inputs, right? Wn xn. After summating all these inputs, I will apply some function. I'll apply some function on top of this input to generate an output. And this output can now be connected as input to another neuron, right? This is the simplest model, right? Remember the model that I explained you here, which is a very, very simplistic model. It's far from the true complexity of a biological neuron. A biological neuron is superbly complex. If you pick up any neuroscience textbook, you'll wonder how all these things evolved out of simple bacteria, right? It's magic. It's magic that nature has created. But let's simplify things. So people said, okay, this is how a biological neuron operates. Let's create a very, very simplistic model with a mathematical structure like this. And that's what Rosenblatt did. And he created the very first simplest form of a neuron-inspired model called a perceptron. We'll see how perceptron works internally. It's, again, remember, this is loosely inspired. This is loosely inspired. This is loosely inspired from biology. When I say loosely inspired, what I'm saying here is it's not exactly a replication of what happens in the biology, right? In the actual human neuron or a monkey neuron, right? There's a lot of complexity happening. They said, how can I build a very, 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 very simplified model? The most simple model that I can build. That's why I'm saying it's loosely inspired by biology. They're not trying to replicate exactly how a neuron works. And we'll see the exact formulation of a perceptron in one of the later videos in this chapter. For now, this is what happened in 1957, and some of the results were very exciting. Then came the era where people said, in biology, right? In actual brains, right? In actual brains, a neuron doesn't exist on itself. A neuron doesn't exist like this, right? This is, let's say, one neuron. It has a lot of inputs, right? It has a lot of outputs, let's say. A neuron doesn't sit on its own. It is connected to other neurons, right? And there is actually a structure around it. So then they said, why should we be limited only by one neuron? Why can't we connect neurons like this, right? Let's assume these are inputs to a neuron. Let's assume these are outputs to a neuron, right? I could have one more neuron whose output goes here, so on and so forth. I could imagine if I'm creating a structure around neurons like this. Okay, so they said, what if I can create a structure like this where, let's assume I have neurons like this. Let's assume I have inputs here, right? This input goes here. This input also goes here. This input can go here. Similarly, let's assume I have another input. This input goes here, and goes here. Let's assume I have another input. It goes to that neuron, to this neuron, and to this neuron. And this is like building a network of neurons, right? Suppose let's assume I have a neuron structure like this, right? Let's assume I have one more neuron. So all these circles here represent neurons. And let's assume these two again now generate something here. So what we have here is a network of neurons. So people said that a typical brain, in a human brain or even in a very small ant brain, right? What we have is not individual neurons. What we have is a network of neurons interconnected. So they said, is there some way for us to actually mimic this network structure? There were a lot of attempts which were made since from early 1960s onwards. Right? Lots of attempts. The first successful attempt was in 1986. Right? There is a seminal research work in 1986 by a group of mathematicians, one of whom is Geoff Hinton. Right? I'll just call him Hinton. But this is work done by Hinton and others, not just by Hinton. Hinton is one of the legendary figures in the whole of modern machine learning. Right? So they came up with this seminal work called backpropagation. It is one of the greatest ideas in the whole of machine learning. So they came up with this algorithm called backpropagation algorithm. Remember, backpropagation algorithm is, in a nutshell, is just chain rule. It's just chain rule. It's literally nothing but chain rule with some simple hacks around it. It's a chain rule of differentiation. Right? It's a chain rule of differentiation. So, but they came up with a very, very nice algorithm to say how to now train these how to actually learn something out of these networks of neurons. So around 1980s, this whole area of artificial neural networks literally emerged, because now we have a network of neuron that we can train. Right? So around 1986, with the advent of artificial neural networks, there was a ton of hype around machine learning and AI specifically, or artificial neural networks. People said there was so much hype that you can't even imagine. People said everything like, okay, in 10 years, we'll have systems which can think like humans, all of this hype. There was a ton of hype around AI. Unfortunately, what happened around 96 was we didn't have enough computational power. We didn't have the computational power that we have today. Today, we can crunch like petabytes of data. Okay, so we didn't have enough data in the 1980s. So even though some of these algorithms are very, very interesting, neither did we have the computational resources, the computational power or data to actually make systems which are extremely powerful. So even though there was so much of hype around AI and neural networks and stuff, all of that died down by late 90s. By late 1990s, all of that hype died down. And that is called the AI winter. That time is called the AI winter because people said, okay, we did all this. I mean, you guys hyped everything about AI that is going to transform the world, but its impact is marginal, its impact is small. So that's called AI winter. When funding from AI, remember, some of the biggest funders of AI were the US Ministry of Defense or Department of Defense. Governments wanted to invest a lot in AI because it gave them superb and very, very interesting applications in military, right? So it's a Department of Defense which funded AI for a long time. But what happened is because of the hype and over-promising in the late 80s and early 90s, right? All that funding dried up when it came to late 90s, let's say 95 plus. After 1995, a lot of that funding dried up. And AI took many, many years to come out of that. Now comes the first fundamental innovation. While many people move to other techniques, you look at SVMs, you look at ensembles like random forest, gradient boosted decision trees. All of these techniques became popular after 1995 up to almost 2008, 2009. Right? These techniques evolved around this period and they became super powerful. SVM became everyone's favorite algorithm around this time. But then people like Geoff Hinton, by the way, Geoff Hinton is a professor at University of Toronto, and he's also a distinguished scientist at Google now, a phenomenal figure. He still believed that to really create human-like intelligence or even great algorithms, neural networks were very important. So while everybody moved to SVMs, random forest, and GPTs, Geoff Hinton did not budge. He said, I can make complex neural networks work very well. So he almost spent from 1986 to 2006. That's almost 20 years of research. He almost spent the next 20 years of his life working on how to make neural networks work better than any of the other algorithms and how to make them scale. So then in 2006, there was this phenomenal paper by Hinton in which he explains how to train. So the biggest problem in the neural network structures in around 86 was if you have, so this is a neural network, right? So how many layers depth it has? So this is typically called the input layer. Let me just introduce some terminology. This is typically called the input layer. This is called layer 1, right? This is called layer 2, right? And this is called output layer, right? So this neural network typically has two layers in between your input and output. So what happened around 96 using the simple backpropagation algorithm that Hinton and others created was, as the depth increases, instead of 2 layers here, let's say you might have 20 layers. Okay, backpropagation used to fail. People understood why they failed, but people didn't have a fix for it. And in an actual brain, we have hundreds of layers. We have hundreds of layers depth. So people realize that to really create great algorithms, we need very, very deep neural networks. People realize that we need very, very deep neural networks. Okay, by deep, what I mean here is the depth, right? You have input layer, right? You have layer 1, you have layer 2, you have layer 3, so on and so forth. Let's say you have output layer here, right? So here you have 3 layers between input and output, right? Imagine if I have 20 layers, how do you train a model like that? So around 2006, Geoff Hinton came up with a phenomenal work where he gave some very interesting ideas on how to train deep neural networks, which is the foundation of all of deep learning that we learn. So deep learning in a nutshell is nothing but deep neural networks. But people didn't take him too seriously, right? There was still, of course, the wave has started when 2006 Geoff Hinton published this seminal work. Frankly speaking, I didn't read this paper till almost a couple of years later, because I was involved in academic work where I was still studying SVMs, random forests, etc. around 2007, 2008. I didn't read Geoff Hinton's paper almost till 2008 myself personally. So not too much of hype around his phenomenal work. But things changed suddenly in 2012. This is the watershed moment. So there is this competition called ImageNet that was conducted by a team at Stanford. Very popular competition. The competition's goal is this. The competition's goal is they created a very big data set of a few million images. And the goal is so it's basically an image data set where you have to detect what objects are there in an image. Okay, it's a very, very hard problem. Till 2012, people use the existing algorithms. Okay, so in 2012, something massive happened. Phenomenal feat, actually. So in 2012, what happened was this ImageNet competition had some error, right? It had some error. So every year, this competition is conducted and they get some error. In 2012, using deep learning or deep neural networks, a team using this large data set. Remember, we have large data sets now. We have large data sets, and using advanced computers, right? Using modern computers with lot of computational power. Right? People designed a simple deep neural network which could beat all other algorithms by a big margin. Right? ImageNet is one of the hardest problems in machine learning at that point. In 2012, it was the hardest problem in machine learning to solve. Because given an image, detecting objects is not at all easy. It's a very, very hard problem around 2012. Right? So what happened was, using these modern data sets and computational power, in 2012, there is the seminal paper where people said, okay, we can do better than every other algorithm by a huge margin. This result made everybody take a look at deep learning seriously. I started reading deep learning ever since I saw this phenomenal work, because my background, I worked a lot on computer vision problems, which one of the sub problems of computer vision is detecting objects in images. When I saw this paper, I was like I was blown out. I was like, wow, this is a phenomenal piece. So from 2012, lot of companies, especially large internet companies like Google, Microsoft, Facebook, Amazon, right? All these companies, even Chinese search engines like Baidu, all these companies started taking notice of deep learning. And they said, okay, deep learning may be the next big thing in computer science. Not just in AI, but in the whole of computer science. And remember, these companies had lots of data. These companies were sitting on tons of data. Imagine the amount of data that Google has, or Microsoft, or Facebook, or Amazon, or Baidu. So they had a lot of data. They had lots of computational resources. So they started developing the deep learning. So because they had both of them, and because they saw this promise in 2012 that deep neural networks can beats classical algorithms by a huge margin, they started investing heavily. So they put their money, their data, and their computational power behind this problem. And from 2012 onwards, it's been the golden days. I would call it the golden days of AI, right? It's phenomenal progress that has happened in the last 5 years, and I've personally witnessed it. That's why I feel so energetic about it. You see tons and tons of research work, again funded by some of the largest corporations in the world, and also by largest universities. Lot of people realized, some of the best machine learning researchers in the world said, deep learning is the next big thing, and we all need to be part of it. Today, if you notice all the great applications, if you notice any of your voice assistants, so you might have encountered voice assistants like Apple's Siri, like Cortana, right? Or Alexa, Amazon's Alexa, or Microsoft's Cortana, or one of the best that I really like is Google Assistant. I use Google Assistant and Alexa on a day-to-day basis. All of them are powered by advances in deep learning algorithms. They would have been impossible without the advances in the last few years, since 2012. All the advances that has happened since 2012 have contributed to all of these great applications. Not just this, your self-driving cars, right? Your self-driving cars that Tesla has, or Google's Waymo has. Google has a subsidiary company called Waymo. All of these are today powered by deep learning. So some of the greatest applications, even in diagnosis, today we have skin cancer diagnosis. We have skin cancer diagnosis using smartphone cameras. All that is powered by deep learning. A lot of modern stuff, a lot of great applications that you have seen in the last few years are all powered by advances in deep learning. But remember, deep learning is not something, some of the core algorithms of deep learning, right, have been there for a while. So there are algorithms like convolutional neural networks, right, which are not very new. These algorithms were there for a few years now. If I recall well, ConNets or convolutional neural networks were there from early 1990s, right? But we didn't have data and computation. Today, the reason deep learning is taking over is, of course, there is lots of data, there is lots of computational resources. Third, importantly, there is a lot of new algorithms. There are a lot of new algorithms that some of the best researchers in this area have come up with. But if you have to rate them in importance, I would rate lots of data as the most important factor, lots of computational power as the second one, new algorithms as the third reason why we are seeing these golden days of neural networks, especially deep learning. So this is a very, very exciting area for me. I've worked on it for a short while on various projects. It's magical. So over the next few chapters, we will learn about neural networks, right? We'll learn the classical neural networks first, the old school neural networks, which became very popular in around 1986. First, let's understand what they are. Let's also understand their limitations. Then we will come to multi-layer perceptrons, which are nothing but our current deep neural networks. Okay, we'll learn a little bit of multi-layer perceptrons, some basic algorithms, and then we'll learn convolutional neural networks and recurrent neural networks. These are some of the most popular models of neural networks that we will encounter and that are extensively used in the industry today. We'll go step by step. This is going to be it's going to be a fun journey. Please bear with me. It's a very, very fun experience. And the first time I read some of these research papers, I was bowled over. I mean, I enjoyed them thoroughly. So I would love to take the same excitement that I have had when I was learning this through all of you, right? And personally, I have seen this evolution. Around 2012 is when I joined Amazon. So when I joined Amazon as a machine learning scientist, I never imagined that 5 years down the line or 6 years down the line, we'll be in this position of phenomenal progress in AI. So I've personally seen some of this happening in front of my own eyes, and being part of it as a customer or as a student, I enjoyed it thoroughly. And now I'll try to take that excitement, or I'll try to transfer that excitement to you while we learn some of these great concepts.